Hello and welcome to the Things Summer Academy. I am JP Meyers and I'll be presenting the LoRa range testing workshop. Shortly after the Things network started, I had my first gateway set up and some devices sent messages through it. But I wanted to know how well this new technology actually works. So I started measuring the distance I get with different gateway configurations and different devices and antennas. Because other users of the network also wanted to do the same, I shared my tools with them. This became what is today known as TTN Mapper. In a previous workshop, you have built the LoRa gateway. Today we will use the Arduino you have programmed to test how well the gateway works and how far a LoRa signal can travel. But first, let's recap on the theory of how radio waves propagate. For now, just listen and take notes. We will get to using the Arduino and gateway in the next section. We are going to simplify a lot of the theory to only the key things that influence range. If you are interested in more, there are YouTube videos available by Thomas Telkamp and Andreas Spies that explains more of the details. I'll provide links at the end. Radio waves travel in a straight line. In this case, we have uplinks from the user to the tower and downlinks from the tower to the user. Radio waves can be blocked. They also become weaker as they travel through different objects. The amount at which the waves are attenuated depends on the material they are passing through and how dense this material is. A tree is less dense than a concrete wall, so a concrete wall will weaken the signal more than a tree. Radio waves can be reflected. Reflections can be good, as it may allow you to communicate around corners. Reflections can, however, also be bad, as a reflected wave is out of phase with the original wave, and can therefore cancel the original signal out. This is also known as destructive interference. For more about this, it's good to read up on the Fresnel zone. Radio waves can be bent, scattered or refracted. This may allow you to communicate across a rocky mountain. Radio waves become weaker as they travel. We call this free space loss. This is mostly caused by the energy spreading out spherically from the origin. Again, it's important to know that radio waves can be blocked, also by the curvature of the Earth. This becomes apparent if you want to communicate at a long range. One important concept when it comes to radio communication is noise, or more specifically, the noise floor. But what is noise floor? It is the hiss or hum that is always present on the radio band. Let's get an FM radio and hear what happens if we tune it away from a radio station. What did we hear? Noise? Yes, this is the noise floor. But where does this noise come from? All matter is built up of atoms, and these atoms have vibrating electrons around them. Moving electrons causes an electric and magnetic field. The warmer the matter, the faster these electrons vibrate, and the stronger these fields will be. Noise also comes from above, from the stars. That's called cosmic background radiation. And all electric appliances have electrons flowing through them, which again causes noise. The combination of all these noise sources causes the ever-present noise floor in the radio spectrum. If we look at the radio signal on a spectrum analyzer, we will see the strength of the signal as a spike in the middle and the noise floor on both sides of it. The signal strength is the height of the peak. The RSSI value is an estimate for this strength. The noise floor is the horizontal zigzag line at the bottom, and the difference between these two is called the signal to noise ratio. For communication to be successful, the receiver needs to be able to hear and understand the transmitter. Imagine you and a friend talking to each other at a music concert. There is a lot of loud music, which is background noise for your conversation. It's quite difficult to hear each other, and normally one will start to shout at each other. It's the same with radio. The signal needs to be strong enough to be heard above the noise. A gateway in a noisy environment cannot hear end devices. LoRa is, however, special, because it can be heard and understood even if the noise is louder, but only if the noise isn't too much stronger than the signal. LoRa signal strength is indicated by the parameter RSSI, or Received Signal Strength Indication. RSSI is measured in decibel milliwatt, or dBm. RSSI is normally a negative number, with a less negative value being better. The minimum RSSI that we would see for a standard LoRa signal is about minus 120 dBm. The maximum depends on how close you are to the gateway, but a signal of about minus 80 dBm is very strong. Anything stronger than this may damage your gateway. At 868 MHz for a 125 kHz wide LoRa channel, the theoretical noise floor is about minus 120 dBm. That's why we will almost never see an RSSI value lower than this. Signal to noise ratio is the second parameter we have to see the quality of a LoRa signal. It is measured in decibels. A positive signal to noise ratio is good, while a negative signal to noise ratio is bad. A normal range for SNR is between 10 dB and minus 10 dB. The RSSI value of a signal will go down when the distance between the end device and the gateway increases. Any obstacles between these two will attenuate the signal and also cause the RSSI to decrease. In both these cases, the noise floor remains the same, which means a decrease in the RSSI will also cause a decrease in the SNR. SNR will also decrease in a noisy environment. If the RSSI remains the same, but the noise floor increases, the SNR will need to decrease. If the signal strength drops below the noise floor, or if the noise floor increases above the signal's strength, we will see that the SNR becomes negative. In this scenario, the RSSI will indicate the noise floor's level and not the signal's strength. To get an indication of the signal strength, we can subtract the SNR from the RSSI. By looking at only the RSSI and the SNR, we can identify a couple of different scenarios. A device close to a gateway will have a high RSSI and a high SNR. A device far away from a gateway will have a low RSSI and an average SNR. A device very far away from the gateway will have a low RSSI and a low SNR. A gateway in a noisy environment will have a high RSSI but a low SNR. Using LoRa, there are a couple of transmission parameters one can change to improve the performance of the radio link. One of the most common ones, which is also used by the adaptive data rate system, is the spreading factor. But what is the effect of spreading factor on RSSI and SNR? A higher spreading factor spreads data out over a longer time period. This means more energy is used per bit of data. If we look at the spectrum analyzer while we increase the spreading factor, we will see no effect on the RSSI. The noise floor is also not affected, so the SNR will also remain the same. But if both the RSSI and the SNR remains the same, why does a higher spreading factor gives longer range? Well, it's because there is more energy per bit. On the receiver side, we listen for longer, gather more energy, and can make a better guess what is said because we have more energy to decide. Mathematically, what we do is an integration, so we sum the energy, and in the process, the noise will cancel out. We can compare this again to two people speaking at a music concert. They end up shouting one word at a time, very slowly. If you are learning a new language, it is also common to ask people to speak slowly so that you can understand. At a higher spreading factor, the signal is receivable in a more noisy environment. What we will therefore see is more signals are received at more negative signal-to-noise ratios. Semtech published this table that indicates the minimum signal-to-noise ratio value that is receivable per spreading factor. The higher the spreading factor, the more negative signal-to-noise ratio is acceptable. Let's have a look at what makes a good and a bad gateway. If a gateway is installed outdoors, there are less obstructions to block the signals. But even outdoors, one needs to install it in a location with a clear line of sight to the area where your devices are installed. Try and install it above the trees and roofs in the immediate vicinity. Some areas are noisy and will deafen the gateway. There's very little we can do about this. Using a good antenna at the correct frequency for LoRa is very important. Height above ground is a double-edged sword. The higher you install your gateway, the more areas it will be able to see without any obstructions. But the higher you go, the more noise is received. Now let's have a look at what affects the performance of an end device. The location where it is installed is very important. Ideally, you want the device to have a clear line of sight path to the gateway. A device on the roof or outside of a building will work better than a device inside the building. A device underground or on the floor will likely perform very poorly. An antenna on the outside of the enclosure of a device will perform better than an antenna inside the enclosure. The orientation of the antenna also has an effect. Ideally, we want both the antenna at the gateway and the antenna on the end device to be vertical. But in practice this is quite difficult, as one can't always choose where and how the device is installed. Choosing a good antenna at the correct frequency for LoRa is very important. Do not use GSM, 3G or similar wideband antennas. Choose an antenna that is specifically designed for 868 MHz if you are in Europe, or the frequency used in your area. An important thing to be aware of is that not all glass is transparent to radio signals. Some glass contains metal or has a metal coating. This metal layer will block radio signals. When installing a sensor in a car, plan to get the signal out of the front window, as these are normally designed to allow radio signals through, while the other windows in the vehicle will block it. This was a quick recap of the most important things to know to test the range of LoRa. If you are interested in more details, have a look at these two videos by Thomas Dalkamp and Andreas Spies. In the next section we will have a look at the metadata of your Arduino on the Things stack console.